In order to use the pressure waves of the thermoacoustic Stirling engine, I would like to use a bidirectional impulse turbine. A turbine offers several advantages over the piston used previously. The origin of bidirectional turbines lies in the harvesting of energy from ocean waves, but the use in thermoacoustic devices was also shown in experiments. The turbine can convert acoustic power into shaft power by redirecting the bidirectional axial flow towards the rotor blades with two sets of guide vanes. The resulting shaft power is converted into electricity by connecting a generator to the rotor. In the last video, I asked you to help me simplify the thermoacoustic engine so that anyone could make it without a specially equipped workshop. Thank you very much for the many very good suggestions, which I now look forward to implementing with you. In the members area, I publish all the drawings and CAD models needed to reprint the components on a 3D printer. The complete models of the turbine are also available for download. The first simplification towards a thermoacoustic engine that anyone can make is to replace the existing piston with a turbine, which is much easier to build with a 3D printer. A turbine also has other advantages. It is virtually wear-free and can be connected directly to the generator without an intermediate transmission. This makes it very easy to hermetically seal the working chamber for use with higher pressures and other working gases such as helium. I also had a lot of problems with the inevitably light plastic piston, which made the test runs more difficult. Depending on the temperature and humidity, the piston was either too stiff in the cylinder or had too much play, which affected the performance measurements. Of course, there are a number of uncertainties with the turbine, such as its ability to self-start. The geometry of the turbine blades is also very complex, and their size may need to be precisely matched to the frequency and acoustic pressures. Over the last few weeks, I have studied the subject and designed a bidirectional impulse turbine of suitable size. A test print with old, not quite dry PETG already looks pretty good. A systematic test with new filament and 0.2, 0.4 and 0.6 mm nozzles shows almost perfect print quality, apart from slightly warping at the tips of the turbine blades. The 0.4 mm nozzle probably offers the best compromise between surface quality and stability. A friend gave me some 6-year-old carbon fiber filament to test, but I am disappointed with its stability and layer adhesion. After clogging the nozzles several times, I will probably have to buy a roll of new carbon reinforced filament to get conclusive results. Printing a brim prevents the tips of the turbine blades from warping, but it's very difficult to remove with PETG. I will have to look for better options in the bamboo slicer or at mouse ears or something similar directly to the CAD model. Other than that, I'm very happy with the print quality and can now do my first tests with a prototype turbine. Everything is working to my complete satisfaction on the very rudimentary test setup. Now I just have to print a housing with guide cones and attach it to the thermoacoustic Stirling engine. I will immediately link all the finished components as CAD files in the members area for reprinting and also add CAD drawings as soon as possible. Thank you very much for watching. Please continue to give me feedback, it helps a lot with the development of the engine.